So the last section in Chapter 8 has to do with when we want to estimate a population mean. So we're talking about quantifiable stuff. So we're going to be looking at a slightly different set of requirements in a slightly different formula. As a matter of fact, a new distribution called the t-distribution. So in this section, we're going to look at the 3 requirements for constructing a confidence interval if we're talking about a population mean. We're going to talk about what a t-distribution is, how it's different from a standard normal, and why it's necessary to use a t-distribution when we're calculating a confidence interval for a population mean. We're going to determine the critical values because we have to use a different table than we can with a normal table, and then we're going to go ahead and once you've got the formula, it's pretty easy to calculate the same way we calculated the other ones. And then we're also going to work backwards and figure out the sample size. These last 2 are going to be in another video because I didn't want this to be too long. So when we're calculating confidence interval, we have a general formula. We have our statistic, and we're going to add and subtract the critical value, which has to do with our percentage of confidence, and then the standard deviation of the statistic. Remember that this part right here, it's called the margin of error. And when we're trying to find the confidence interval for a proportion, our statistic is that sample proportion, or p-hat. We're going to add and subtract to the z star. And remember, the z star is calculated by looking at the normal curve, centering our percentage in the middle, and then taking the z of the tail. Then we're going to multiply it by the standard deviation of the statistic. That's all well and good, and if we're going to move to means, it makes sense that you can just go ahead and plug in what we already understand. Our statistic wouldn't be a proportion, it would be a mean, and then we could add or subtract the z star, and then our standard deviation of the statistic would be the population standard deviation divided by the square root of the n. Well, that's all easy, except if we're looking for the population mean, we probably do not have the standard deviation. So there's got to be other ways we can do this. So if we don't have the population standard distribution, we have to use something else for the standard deviation of the statistic. So we can go ahead and use the standard deviation of the sample. Remember, that's the value minus the mean of the whole thing squared, plus the value minus the mean, whole thing squared. Add them all together, divide by the total number of things in the sample, and then take the square root. We're going to find, however, that when we standardize this distribution, it's not going to follow a normal curve. So when we're calculating a z-score, we're standardizing, we're getting a standard score. And what that z tells us, it takes the actual values and puts them into their relationship to the normal curve. So a standard curve, a 0 is where the mean is, and then 1 is 1 standard deviation away, and 2 is 2 standard deviations away, etc. And we have a lot of knowledge around that. We understand that 68% is between 1 and -1 standard deviations, all that kind of stuff. So there's a lot of information we know about the standard normal curve. But if we're going to use the sample standard deviation instead of the population standard deviation to calculate what kind of distribution are we going to get and what happens when we standardize. So this is what. So here's one we're really familiar with. When we standardize, get the standard score here with z, the distribution is very much a normal curve. And we've got a peak at 0, and then 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. The t, which is the mean minus the population, sample mean, divided by the sample standard deviation over the square root of n, it doesn't have the same distribution. It is much like normal. It's symmetrical, it's got its center at 0, but it has much more area under its tails. And the shape depends, the shape very much depends on the sample size. So when we talk about a t-distribution, we're going to talk about very much the degrees of freedom. That relates to the n, and we calculate that degree of freedom by n minus 1, since the shape changes depending on the degree of freedom. So the standard normal curve is the top one in this picture. And you'll notice that the t-distributions start to flatten out as the degrees of freedom get smaller. The spread of a t-distribution is always bigger than a standard normal distribution, and a lot more probability in the tails and less in the center than normal standard normal, particularly as the degrees of freedom get smaller and smaller. So when you're thinking about so many standard deviations away, it'll be a higher number. The t star will be a higher number than the z star might be. So since we know that we're going to need to use a critical value of t star, we can get that information from a table. We can also get that information using our calculators. But table B, which in your packet that you're going to get on the AP test, is right next to the table that we use for normal curves. You just need to pay attention to two things. We have to find the confidence level, and once we have the sample size, we're going to find the degree of freedom, which is just one less, and then we just go ahead and find our confidence level, find our degree of freedom, and move across till we find that critical value. Just so you know, 95% confidence level leaves you with 5% to split up on the two tails, and here is that probability. That's what that top part means. But this table is going to give you the critical value, and then if you were going to use technology, you do have to pay attention to this upper tail, and you would go ahead and use inverse t, and you put the area of 0.025. Whoops, that's really messy. The area of 0.025, and then you would put the degree of freedom, and then it'll calculate it for you. So there are a couple of things you need to pay attention to. There's not a degree of freedom for every number. So in this case, there's 48 observations, or a sample of 48, an n of 48. But the closest thing is 50. But when we're looking for critical values, we want to ensure that we're actually getting the percentage that we want. So you're going to take a critical value that is the closest one lower than it. So 48 minus 1 would be 47, but the closest one that's lower than it is 40, so we would use a 1.684 as our critical value. So before we can make a confidence interval for population means we have to check some of the same things we check for a proportion. It has to be random. If it's not a well-designed random sample or a randomized experiment, we cannot calculate a confidence interval. If it's the sample is greater than 1/10 of the population, or as we've been talking about it 10 times, the n has to be less than the big N. Same. This one, we have to look at the normality of the actual population. So if the population is normal, we'll go ahead and go. We can go ahead and use our T procedures. If the sample size is large enough, we can go ahead and go. Because remember, even though a population can be skewed, its sample distribution will become approximately normal when the sample size is large enough. But if we don't know the shape and n is less than 30, then we have to actually look at our sample data and graph it to see if there's any obvious skew or outliers, because we cannot use T procedures if the graph shows them. Now, when you are doing a free response problem from the AP test, they're going to give you ones that meet all the requirements, but you do need to show that they meet all the requirements, even if you can move ahead and go forward with the T procedures. There might be some questions on the free response, however, that have you look at the skewness of a thing, and once it says it's skewed, you know that you can't make a confidence interval. So we've met our conditions for inference, and we know that the sampling distribution is roughly a normal distribution. But because we don't know our population standard deviation, we have to use our sample standard deviation. But we found out when we standardize sample standard deviation, we end up with a different kind of distribution. So how this all rolls is this is our new piece of information that we're going to replace this with in our formula because we don't know this. And then because our distribution is a t distribution, we can't use z-scores to allow us to find our z-star. We're going to have to use t-scores to find our t-star, or in our case, we're going to use tables. So you're going to take your statistic, and I'm going to blow this up. No, I'm not. We're going to take our statistic, which is x bar, and then we're going to go ahead and add and subtract the critical value of t star and our standard deviation of the sample divided by the square root of n, and that will give us our point estimate and our margin of error. So if we are finding the interval for a population mean, unless for some reason we have the standard deviation of the population, which would be very rare, we're going to go ahead and use this formula, assuming it meets all of the conditions. And the only part of the notation that we haven't talked about yet is you find the t star in the critical value for a t n minus 1 distribution. So that's related to the degree of freedom. And so if the degree of freedom, the n is 10, the degree of freedom is going to be 9, and so we're going to call that a t of n minus 1 distribution. So we'd be talking about the t of 9 distribution. But that notation, I don't think you're going to really have to know very much. You just need to know this and what each piece means and how to find your t star and how to find your s, your standard deviation, etc. So that's the basic stuff about the population mean, the long story about how to get to that formula, and then it's just really a matter of plugging the numbers into the formula. And then in the next video, I'm just going to explain how we actually do the calculations as well as how to work backwards to obtain a C confidence interval. To figure out our sample size if we wanted a particular percentage and a specified margin of error. So that'll be in the next one.